Morning, everyone. We will make a start on our HIPCAN webinar this morning. So welcome. Just a few housekeeping points to start with. If you could all keep your screens off and microphones off during the presentation. We've got 4 presenters for you this morning. Yeah, I can't, there we go. And if you have any questions, could you please put them in the chat and we will get to them at the end. The presentation should last about 40 minutes and then we've allowed 20 minutes for questions. You've got 4 speakers this morning. We've got Steve Newbury, Managing Director of Ultima Forma, Michael Parsons, Senior Research Engineer at the MTC, Andy Bushby, Chief Technology Officer at Ultima Forma, and John Schofield, CEO of Acantex. The session is being recorded as well, so just to make you aware of that. So I will now hand over to Steve Newbury.
Thank you, Kerry. Good morning, everybody. Thank you for joining. So the focus of today's webinar is on PMHIP, specifically around innovations in using electroforming to manufacture HIPCANs, and we're going to use a project that we've done together with UKAEA to be able to explain some of the innovations that we've had over the last couple of months. It's worth saying that there are other manufacturing methods for HIPCANs, but today's session is specifically focused on electroforming. So Ultima Forma, we're a UK-based material science and advanced manufacturing firm. We have deep expertise in electroforming, and we're using this to produce a range of different products for advanced engineering firms, and some of the technologies that we've developed have been transferred into hipping, for example, being able to use that to create barriers to hydrogen systems, for example, which we have a patented process for, and this enables us to create helium leak tight vessels for hipping. So there's a range of other different well-known manufacturing processes for manufacturing metallic bulk components, but hipping has a number of specific advantages, which are listed here, but the main ones being that we can leverage advances in powder metallurgy and designer materials to create sort of products with superior performance that can be used in a number of demanding engineering applications, and specifically where eliminating porosity in components and inclusions is specifically highly valued. So typically hipping is used to produce advanced components using high performance alloy systems, and here's some examples here that are commonly used, and as I say, the applications for these typically cross over between aerospace, the energy sector, and high-end kind of medical and industrial applications. So some of the key advantages of using electroforming to produce a HIPCAN are specifically where complex geometry is required, and the other speakers today will talk more about that in their own slides. One thing that's particularly interesting for me is how we've brought together innovations in hipping with powder metallurgy and with electroforming together, and how when you bring together innovations across different areas, this is how we can unlock new capability in terms of manufacturing. So I think that's what's particularly novel about the approach that we've taken. So handing over now to Michael Parsons from the MTC, who have manufacturing capability and a deep interest in hipping. So over to Michael.
Cheers, Steve. Yeah, so like I've said already, I'm Mike. I'm from MTC, and I've been involved in hipping for about 10 years now. Yeah, and MTC is part of the High Value Manufacturing Catapult Centres. We opened in 2011, and our aim is to positively impact society through manufacturing and technologies. We do that through essentially trying to bridge what we call the valley of death. So working on the technology and manufacturing readiness levels that sit generally between university, academia, and in entrepreneurial sort of setups and traditional industrial research and development. So we sit there in the middle to try and push technologies along. The areas that we work in are on the next slide. Thank you. So we have a transformational industrial transformation team. Got a digital team which looks at modeling, simulation, metrology, and big data, things like that. Industry 4.0. The advanced production systems team, they work in anything along the lines of automation, robotics, and designing and building bespoke equipment. The team I am part of, or the wider theme anyway, is the component manufacturing technology team. We have additive capability, so metals, ceramics, polymers. We look at laser processing, so laser peening, cutting, texturing, and welding. And then I'm part of the materials technology, where we focus primarily on powder metallurgy, on material formulations, circularity, and a few other things too. And there's also a future skills side, so looking to develop the next level of engineers for the future. As I mentioned, we're part of the High Value Manufacturing Catapult Centres. There's a range of catapult centres across the country, which you might be familiar with. MTC's got 3 different sites, one up in Liverpool, Coventry, where it's our main base, and then down in Oxfordshire, which is a training site. So HIP, moving on to the next slide, if that's all right. What's the point of it and what is it? We've covered it very briefly, but it's applying uniform high pressure, high temperature gas. It's used for a range of different things. It can be used to densify additively manufactured parts or castings, so essentially removing the pores from the center of those. What it won't do, sadly, is remove those on the outside of the component. So anything that's exposed to the HIP gas, it won't be able to remove, but anything that is within the part, it can densify and improve those properties. You can use it to form through powder HIP, as has been said so far. For that, you need a metal canister or a canister of some form, typically metal, which seals your powder within, and the HIP gas compresses that. It's quite good for replacing forgings, particularly ones that have got long lead times or poor material efficiency, because we can go more net shape. It's also good for replacing castings. Again, because we're going net shape, you can get a more similar sort of net shaping to castings if you work on it, but you can get much better performance. And you can also use novel materials. So there's materials out there that are better to use through HIP, or materials that are only really available in powder form and therefore make sense to use through the HIP processing. And the way that those powder particles stick together as they're pressed using the HIP gas is through diffusion bonding. So you can use that to join those powder particles, but you can also use it to join large components, solid components. So you can have dissimilar materials being joined through the diffusion bonding process. You get high integrity joints with quite a thin diffusion layer, so there's not a lot of movement between those. And you can also get very high complexity joints if you want to through the HIP process. But back to powder HIP. Conventionally, most organizations will use steel or another sheet metal, or potentially tubes. It means these canisters are pretty low cost in terms of their materials. They've got a good high strength to weight ratio, and sheet metal in tubes are pretty versatile in what you can make. So there's an example there of an oil and gas situation where we've got a valve body. We've designed it so you can see the modeling there on the left. In the center is the actual component we've done, and then afterwards is the post-HIP compared to some of the modeling. The challenges though with metal, sheet metal, is firstly complexity. So the more complex you go, the lower your processing or post-processing and the powder costs will be. They'll start to go down until they get to a certain level where you just need the exact amount of material that you need. But as you go more complex, depending on the complexity of the final component, your canister will increase more and more and more. If it's a relatively simple component, that might not be very much at all. You might have a sweet spot where you can go almost completely net shape. If not, then, and the component is very complex, then the more you go towards that, then the higher the complexity of the canister will be, and actually you might get to a point where you don't want to proceed any further, and the sweet spot is a bit earlier on. Similarly, if we're just, all right, to go back up again, sorry, to the previous slide. There's likewise with these components, if you're doing sheet metal fabrication, you can be limited by the volume of production that you're going to do. You need an experienced welder because each part needs to be welded and needs to be welded to a very high level. Sheet metal fabrication is generally low in terms of manufacturing tolerances, and typically we sacrifice the canister so it's pickled off or machined off afterwards. But on the next slide, there's a couple of different ways that we can manage this. So we can integrate the canisters into the final component, use internal space holders. There's some novel processes that are interesting, and then you've got advanced manufacturing of complex cans, which is what we're talking about today. So in terms of integrated canisters, so you can use that diffusion bonding process to diffusion bond your canister in place. So for instance, a corrosion resistant layer, a welding feature, or some kind of structural feature that might not be useful to make out of powder. So you can see the example there of being a steel valve body that we've produced. These are typically lined with Inconel, and on the left there is a component that we've both formed through powder hip, but also clad with an Inconel layer. On the next slide, we've got another example where the canister is made of stainless steel, and the powder is copper chrome, so down there on the bottom left. You can do curved features in there, so you can see its intersection just to show the curved geometry. This would be challenging to make. So you've got your corrosion resistant layer, but you've also got a process, a geometry, sorry, that would be more challenging to machine otherwise. In that top right, you can do powder bonding. So we've formed copper chrome zirconium powder into a component at the same time as Urethane 97, so two very different materials. And on the bottom there, we've used a canister with an additively manufactured component as part of it. So most of it was sheet metal fabrication. We powder hip the copper chrome zirconium on the bottom right to that additively manufactured part, which is part of the canister. Then the second side of stuff is this complex internal features. So rather than making the canister more complex, you could add complex features to the inside. So using space holders, using internal canister features, some hybrid methods, and some multi-stage hip diffusion bonding, which we won't go into today. The advantage of this is you can get that high complexity without adding the cost complexity to the canister. So you can reduce your machining times and you can add novel features. So here is a component where we've used soluble space holder materials in a titanium component to make both voids inside the component, which would be very hard to do through another process, and also porous structures at the same time, just using essentially conventional table salt. On the next slide, we've got a higher temperature application with dissimilar material bonding, so copper chrome zirconium to tungsten via a copper interlayer. This is producing a relatively complex heat sink cooling feature, just using conventional manufacturing, conventional machining, laser cutting, and 3-axis machining of the copper chrome and the copper components, and filling that then with a soluble space hold that we can remove at a different temperature, just using water. And then here you can use the canister itself as a space holder. So the top there, you've got a copper chrome component with the bent cooling features. So showing just that you can do features that are more challenging to do through normal manufacturing. And at the bottom, we're taking this a step further where we've added a curved tube that would be hard to do anyway through conventional manufacturing. And then we've added rifling features to that. So when we powder hip that component afterwards and then pickle it later, the powder hip component has essentially a rifled feature that works through for advanced cooling distribution on a curved geometry, which is incredibly difficult to manufacture in another way. There's other ways to do this as well. So we mentioned novel approaches. So a group called Grid Logic we've worked with does essentially an additively manufacturing kind of process within the HIP canister. So layering those powders in the right place and then hipping the mitre on. So we've worked with them to do multi-material layering of a titanium component with different types of titanium in there and different types of blending, so that we also have porous features integrated into that. So you get essentially an additively manufactured component in terms of complexity with the integrity of a HIP component and additional features like control porosity. And then lastly, we come to complex canister manufacturing. So this is the sort of focus of the rest of the webinar. You can do this a few different ways. So additively manufacturing a canister, it's generally quite costly for many processes, but cold spray is one way of doing this. So at the top there is a copper component that we've cold sprayed. You can rapidly produce canisters in that sort of process. It's not the most beautiful part, but it is a proof of concept to see whether this is a viable method. Laser powder bed fusion is another one. So like I said, we've used that more for inserts or adding cladding onto those components rather than making the canister, because it's a more expensive process. But others have used wire arc additive as a process for making complex components. Incremental forming is not so much an additive process, actually. It's in the wrong place, but it's actually a forming of sheet metal that can produce very complex components. And then the last two is advanced casting. So MTC has worked with companies before looking at producing canisters that are from a casting formation. You can do very high complexities through those. They've got their challenges, they've got their place. And lastly, electroforming, which is where we talked to Ultima Forma. We approached Ultima Forma to produce here on the far right there at the bottom a component similar to a rocket nozzle in nickel. So it's got curved organic features that would be, if we made that through sheet metal, it would be multiple components, have lots of welding. Each weld point is a potential leak rate, a leak risk. And also we've added features on there that would be more challenging to do as well. So at the top and the bottom, the surfaces and the final component will want to be flat. If we add them as a flat feature to our canister, the HIP pressure will bow those in slightly because the edges are stronger during the HIP cycle. Whereas actually what we've done is we've billowed them out. So during the HIP cycle, that deformation is changed and it will approach a more flat component by the end of it. At that point, I'll hand over to Andy to talk a little bit more about the electroforming process.
Of new technologies, and now, as Michael said, we're going to focus on the electroforming. So I'm going to introduce that, and then I'm going to introduce the UKAEA Fusion Futures project, where we did a proof of concept to show that how this would work. So in electroforming, metals are deposited from an electrolytic solution containing those metal ions onto a surface or a mandrel. It's an additive manufacturing process, building the material from the inside surface outwards. And you can keep going like that. So the metal continuously builds up over time from micrometers to millimeters in thickness. The mandrel controls the internal shape of the part. And then if you remove the mandrel, you are left with a hollow part that would form a HIP can. Thanks. The mandrel then is crucial to the electroforming process, and there are lots of different ways that you can make a mandrel. If it's going to be removable, typically we use things like waxes and thermoplastic polymers that can be removed by heat or solvents. But you can also use things like low melting temperature metals. And of course, 3D printing is a technology that allows us to access all kinds of new shapes. But they can also be cast, machined, fabricated. And as Michael suggested, you can also incorporate into that mandrel all kinds of different components, different features, or indeed, other materials that are already preformed. The electroforming process flow then starts with the mandrel. So that's going to define the internal shape of your part, the surface finish, and any features that you want to incorporate into the part. If the mandrel is non-conductive, you have to make the surface conductive by electroding it. There are a whole range of processes for doing that. There are metal particle sprays that we can use, graphitic sprays, electroless processes that are widely used in the plating on plastics industries and electronics industries, or you can even go to things like physical vapor deposition to deposit an electrode. Once you have a conductive mandrel, you then go to the electroforming process, which is a bath of electrolyte, essentially, with an electric field through it, build up your metal over time, and then either remove the mandrel to create the hollow part, in this case a hip can, or retain the mandrel to form a hybrid material system. Thanks. The kinds of materials that you can typically electrode deposit are things like the transition metals and the noble metals. There are some alloys that can also be formed by co-deposition, but for hip cans, typically we're talking about the transition metals deposited onto polymer or wax or resin substrates. But that could also incorporate other parts, other metal parts into the component. So your can forms an integral part with another component. Okay. So the advantage of an electroform canister are that we now have complex shapes and features that we can incorporate into the can readily, and we can use a digital design to manufacture process, which means we can turn around a design much more quickly and go from an idea to a hipped part in a shorter timescale, and then of course iterate that design if we find that there are features that we want to create. The can itself is continuous and smooth shape. So as Michael explained, it means that you can accommodate the shrinkage of the can and the powder during the hip process. And of course, we can model that shrinkage and design the can to end up much closer to the final component that we want. There are fewer welds to incorporate. Potentially only the fill tube needs to be welded, but there's no reason why you couldn't electroform different parts of a can and weld them together to make a very large component with complex features. And there's the potential to leave the can on as part of the final product. So when we deposit metal by electrolysis, it's pure metal that we're depositing. It's 100% element, so you know exactly what you have on your surface. Electroforming is an automatable, scalable process. We do that here in our facility in the UK. It means you can have faster turnaround of parts. You can do very large parts with complex geometry. You just need a bigger electroforming bath. It can be the size of a swimming pool if you want. And you can parallel manufacture, so you can produce multiple numbers of parts at the same time. And that lends itself to mass manufacturing. So now I want to introduce the UKAEA funded Fusion Futures project, which was a 4-month proof of concept project with collaborative partners, including ourselves, Acantex, who will join us in a second, and Advanced Manufacturing Limited, who did some measurement of the cans to quantify the shrinkage and the shape deformation of the can. And the objectives of this project was to design a demonstration shape that incorporated some of the features that are very difficult to incorporate into a hip can, produce a bunch of hip cans, fill them with copper chrome zirconium. So this is of interest to fusion applications, a pure copper can and a copper chrome zirconium alloy powder, and then assess how that process went. So we designed a can using CAD design with some features that are very difficult to traditionally incorporate, off-axis features, ribs on the surface, and so on. We model the anticipated shrinkage of the powder, so how it's going to behave once it's consolidated. And then we use 3D printing to create a wax preform. So again, we're borrowing some technology from the investment casting business, where it's now possible to 3D print investment casting waxes. and then we electrode that wax with using the electroless copper process, which again we're borrowing from the electronics industry. So we're bringing together different technologies here to create some innovation. In the project, then we created a bunch of HIP cans in pure copper. So you can see we've got 7 cans here, all made on the same type of mandrel, all the same. Essentially, we changed the thickness of the can to see how that reproduced different kinds of features and whether it would survive the hipping process and the other process steps. You can see from the outcomes that we successfully hipped 3 of the cans. They were typically the thicker walled cans, around 1.5 to 2 millimeters in thickness, and that allowed us to be able to produce a fully hipped component. So I'm going to hand on to John from Acantex now to take us through some of the ins and outs of that process and what actually happened during the hipping. Thank you, John.
Yeah. Thank you, Andy. So just a very brief introduction to myself and the business of Acantex. So it's been established since 2022. So we've been around for a short period of time, but during that time, we've made quite a significant number of cans from various means, various ways, as Michael explained. You know, so we've used 3D printing, traditional fabrication methods, etc. So this was our venture, if you like, the first venture into electroforming, and the results were really quite positive. So I think that's really positive. So next slide, please. Yeah. So this, if I take the opportunity just to highlight a couple of points that have already been made, but really I think the graphic on the left quite nicely explains it. So this is a case study that was done in the manufacture of a 7-kilo aerospace ring, and you can see the other traditional methods are starting with a significant amount of material to make a 7-kilo ring. So the PM HIP one on the right hand side of the graphic starts with significant less material. I mean, up to 85% less material than a traditional method. So that has a number of benefits, obviously from a cost perspective, but not only that, it's got better environmental credentials, you know, etc. But also from what Mike was saying earlier, you know, reference to the benefits of grain structure, etc. So you've got better thermal stability, better high temperature performance, and as the market is trending more to near net shape manufacturing, it opens up quite a significant opportunity for this, you know, in the various methods of manufacture. One thing other to note is the lead times. You know, in terms of these parts, they're relatively short lead times compared with the forging. You know, forging lead times can be anywhere up to from 26 weeks to 52 weeks, which you wouldn't believe. You know, so yeah, so it's much quicker delivery of these parts. So again, this just highlights the benefits again. So if you look at the micrographs on the left, you can see the different grain structures. Looking at casting to wrought to PM HIP, you get a much more evenly distributed properties of the material, so you get much more isotropic properties. And the table on the right was a case study that Deloro Stellite performed on a cobalt-6 alloy, ironically, and you can see that the PM HIP performance is better than the best of the rest, you know, so in terms of tensile strength, yield strength, tensile elongation and Sharpie impact test, it scored very good, you know, better than the rest on the other technologies. So we were kindly we were asked to participate in this in the project, the Fusion Futures project with Ultima Forma and the AEA and AML, which was a great opportunity for us to explore, you know, innovative technologies in canister manufacturing. So so we're thankful for the ability to participate in this. So this graphic just explains the process. So what we're talking about here really is the canister manufacture. So as as Mike and Andy have said, there are numerous methods to make canisters, but ultimately, once that canister's made, the process after it is very similar. You know, so you leak test the can to make sure it's hermetically sealable. You then fill that with a metallic powder. The process is quite agnostic, so providing the can material is suitable, you know, you can use a large number of different metallic powders. You then vacuum degas the can effectively to remove atmospheric nasties, and then you crimp and seal that canister, and then apply heat and pressure through hipping, which Mike explained earlier, and then the finished product is at the end of it. So clearly, the nearer to the net shape you can get, the better from a material perspective, you know, environmental, etc. So just concentrate on the process we did. So we leak tested the cans. So as Andy said, you know, we started off with 7 cans, and we found there is, you know, some minor issues with leaks, but we ended the process with 3 cans that achieved very good leak rate scores. So you can see on the right hand side picture, you know, that one in particular was in the sort of 6.4 times 10 to the minus 11 millibars per litre second. So it's really good score. So each canister was tested with helium, just to obviously ascertain if it was suitable to move on to the next process. So from that, we filled the canisters and then degassed the canisters. So we used copper chrome zirconium powder, as Andy mentioned, and we vibrated the canisters to ensure that the extremities of the part were filled, and then we vacuumed the cans into a relatively low vacuum level, so you can see on the picture. So this particular can was vacuumed down to 3.6 times 10 to the minus 3 millibars, which is suitable for this process. The picture to the right just effectively shows the crimping and sealing of the canister after degassing. So the cannons were hot isostatically pressed at the Royce Institute. So once we'd filled and degassed and sealed the cans, they went to the Royce Institute, and you can see a couple of pictures on the bottom which show comparisons against so it's the post and pre pictures. So obviously you expect shrinkage, you know, in the canister, and you can see the deformation of the filling evacuation tube also. So we got, you know, good results on the 3 cans that we got to this stage of the process. The chart on the bottom right effectively just shows the cycle that was used. So we used quite a conservative HIP cycle to perform the consolidation on these cans. So we HIPed at 800 degrees C and 100 megapascals, really to protect the can, just to make sure that we could, you know, increase the probability of success. And the cans performed really well, to be fair. So, you know, on the next, you know, for the next round or the next stages of development, we would look to increase the temperature nearer to the melting point of the material, yeah, and also the pressure, the HIP pressure, to increase the consolidation percentage. So in terms of learnings, again, we've talked about this a little bit earlier, but the shape at the end of the process was remarkably similar to the beginning, as you would expect. The shrinkage of the can was quite evenly applied, which again was good. It showed, you know, so it suggests the predictability of the end shape. It was very positive. We did encounter some issues with the wax mandrel material. On this slide that you saw earlier, the wax melted out at 720, I think it was, degrees, and it created an issue with thermal expansion on some of the parts, which we managed to recover with welding. And as Andy suggested, the thicker cans performed better. So, you know, somewhere around the 2mm thickness worked really well. And it did highlight that copper was a very good material to and very suitable to the electroform process. So I'd like to hand back to Steve to finish up the Ultimaform presentation.
So before we move on to any questions, here's just a summary of some of the kind of key findings from the project. So these are areas that we feel that have opportunities for the future, and some of the kind of benefits over the other processes. So genuinely using electroforming to produce HIP cans can reduce the amount of powder that's required in the first place and reduce the amount of post-HIP machining, which all has kind of value in terms of reducing cost, but also time for the overall kind of manufacturing process. So yeah, those are kind of key benefits. In terms of the kind of next steps, so through the work that we've done so far, we've established that we have a proof of concept component that we were able to manufacture, and a process that was able to be validated, but there's always kind of more to do to optimize the process and optimize the design of the component and build in more complexity and more design features that will be valuable for industry. So we're particularly keen to engage with across industry to understand where people are thinking that perhaps HIP might be a suitable candidate process for components or new designs that they're working on, and allow us to provide some kind of initial feasibility as to whether HIP would be a good process and what the specifics of that process could be for individual components and manufacturing volumes and target piece costs. So thank you very much. I'll just hand back to Kerry to facilitate any questions.
See if we've got any questions. I think we've got any questions at the moment. Has anyone got anything they'd like to put in the chat?
People can raise a hand.
Yeah, or raise a hand. Oh, stunned into silence. Anyone? Q&A, hold on. So Kieran has asked, what work is being done next on improving mandrel removal?
Okay, let's speak to that. So the question is, what can be done about improving the mandrel removal? And we're currently investigating a series of specialist waxes that would be not only easily shapeable, but more easily removed at a lower temperature with a cleaner kind of burnout, because we don't want to leave any carbon residue on the inside surface of the can. So we've got some ongoing work here at Ultimaform to investigate a better solution. In some other applications, we do use thermoplastic polymers as well, which wash out quite readily in solvents. So depending on the numbers of components, on the complexity of the shape, there are a range of different routes that we could use to develop a suitable mandrel for a particular component. There's a diversity of different ways of doing that. So thank you for that question.
Any more questions from anyone? We're happy to share these slides if anyone would like them. We've got your email address, so maybe just say if you didn't want them, but we're happy to share them. Job done.
So, yeah.
Great. Kieran said, yes, slides would be great. Lovely. Oh, hold on. Any further questions? If there's any more. Okay, Charlie. Charlie, yes, we can send the recording out to the rest of the team.
So,
Yeah.
certainly.
Oops, I'm going to help you if I turn my camera. Thank you, Will Purpry at the Royce Institute HIP facility in Sheffield has asked, do we have an estimated time for CAN creation? And somebody else has liked that question. Thank you very much. What would it take to create a CAN? So assuming you've got a design, currently it would take about 3 weeks from start to finish to turn that round to a HIP component, and we'd like to push that down in the future to a week turnaround. It's quite ambitious, but I think it's potentially possible going forward as these technologies mature. Once you have a CAN design proved out, there's no reason why you can't manufacture them in parallel, and we have some developments here at Ultima Forma to create a mass manufacturing process where every part comes out the same, and that would allow you to produce, you know, hundreds of cans per month if that's required, and we'd set up a dedicated process to do that. So I hope that answers your question, Will. Need a bigger HIP to put them all in.
We've also got Michael has raised his hand. Michael, did you want to ask a question or?
More of just a comment. So I just wanted to, on behalf of the United Kingdom Atomic Energy Authority, thank the consortium partners for the excellent work you did on the project. It's really interesting, as well as the comments by Michael Parsons here at the MTC. These are technologies that are potentially very useful in our sector in expanding the tool set of available manufacture for these complex geometries that have to go into sort of high performance applications. But we're also very keen for people from other sectors. If you want to come talk to us about where we could use these technologies and partner with you to develop them with organizations such as Ultima Forma and Acantex and AML, that would be fantastic. So yeah, it's been a really exciting project, and I really look forward to doing more. But yeah, and then, as I say, I'd encourage opportunities from other sectors to come talk to us in Fusion, because the challenge we face is that we're developing these technologies for something that we're not ordering quite yet. So if there's others who'd like to partner with us to support and fund the development of these technologies, please come talk to us.
Okay, I think we might have a. What materials are next on the horizon for electroforming?
Another one for me.
Kieran, yeah, from Kieran.
Oops, please. Okay, thank you, Kieran. The question is what material systems are coming onto the horizon. So we can already in the UKAA project, we've made a copper HIP can, because that's a fusion allowable material and suitable for consolidating the copper chrome zirconium heat exchange material. You could also use copper cans to consolidate aluminium alloys at lower temperatures, potentially. We've also made nickel HIP cans already. We also have a process at Ultima Forma to deposit iron, which is pure iron rather than steel. But that also allowed us to create you could potentially put the inside of the HIP can in iron and build the outside in nickel or some other high temperature material. It's possible to deposit cobalt by electrolysis. It might be an expensive component, but that if you wanted to leave the cobalt on the outside of the can, that will be possible. We can also deposit nickel cobalt as an alloy, which has very good corrosion resistance. So again, if it's the outside surface of the can, and then combining those technologies with diffusion bonding or with other components is another potential application. So I hope that answers your question, and hopefully you'll see some of those application potentials coming out through our collective publicity lines through our website and LinkedIn over the next year or so. Thanks.
Excellent. If there are no more questions, then we will finish the webinar and we'll share the recording and the slides with you all. So thank you very much. Thank you.